Let's do some numerical on elasticity. See this question. Two blocks of masses 1 kg and 2 kg are connected by a metal wire going over a smooth pulley as shown in figure. The breaking stress of the metal is 2 into 10 to the power 9 Newton per meter square. What should be the minimum radius of the wire if it is not to break? See, we have to calculate first tension. What is the tension in the wire? And then from tension we can find the stress. And we have to see that that stress in the wire should not exceed this value. So first of all, let's find tension. Suppose the acceleration of the block is A in this direction. So acceleration of this block will be A in upward direction. So if I draw the free body diagram of 1 kg block and this 2 kg block, then what are the forces acting on 1 kg block? You have T in upward direction and 1g in downward direction. You have T in upward direction and 2g in downward direction. Acceleration A in downward direction and this acceleration A in upward direction. Since acceleration A, you have acceleration is A in downward direction, so net force in downward direction is 2g minus T, and that should be equal to mass into acceleration. Here net force in upward direction is T minus 1g, and that should be equal to 1 into A, right? So this will be G equals to, yes, so we get from here G equals to 3A. So A is G by 3. A is G by 3. Alright. Acceleration is G by 3. So acceleration is G by 3. So if I put it over here, that will give you T. T is G plus A. So this would be sorry 4g upon 3, and if I put the value of G equals to 10, so it is 40 by 3 Newton. That's the tension. That's the tension, right? And if I want to calculate the stress is tension upon cross section area, and this should be less than or equal to 2 into 10 to the power 9, right? So less than or equal to this, and that gives us pi r square equal to 2 is greater than or equal to 1 into, or r square is greater than or equal to tension upon, and tension is known to you, 40 by 3. So r should be greater than or equal to under root of this. So that's your R min. If you go below this, then the wire is going to break. The stress will be higher. If you go below this, then this will be very, very small, and this will go very high. This will go higher than this. In that case, the wire is going to break. So you just solve this. Just solve this. You'll get the answer. The answer is 4.6 into 10 to the power 5 meter. That should be the minimum radius. That should be the minimum radius. Okay. Fine. Let's move to next question. One end of the metallic wire is fixed to the ceiling, and the load of 2 kg hangs from the other end. You have this is ceiling, and you have a metallic wire, say you have a metallic wire over here, and to this metallic wire we have a load of 2 kg hanging. A similar wire is attached to the bottom of the load. You have a similar wire getting attached at the bottom of the load, and another load of 1 kg hangs from the lower wire. You have 1 kg hanging from the lower wire. Find the longitudinal stress in both the wires. Area of cross section is given to you. Young modulus is given to you. Okay. Fine. Longitudinal strain. You have to calculate strain. Area of cross section is given to you and Young modulus is given to you. So if I calculate the stress in each wire, then stress upon Young modulus will give me the strain. Right. So let's calculate the stress, and before calculating stress we have to calculate tension in both the wire. We have to calculate tension in both the wires. Suppose tension in this wire is T1 and tension in this wire is T2. Now both the blocks are in equilibrium. So if I draw the free body diagram of these blocks, then you have T2, T1 below and 2G below. Over here you have T1 and 1G, right? There is no acceleration, so T1 minus 1G is 0 and T2 minus T1 is this. So T is 10 Newton and T2 is 30 Newton. Alright. So if I calculate the stress in wire 1, the stress will be here. Second wire would be 30 upon cross section area. Cross section area is how much? 0.005 into 10 to the power minus 4 meter square, Newton per meter square. And once I calculate stress, I can calculate the strain over here. Stress upon Young modulus. Stress upon Young modulus. So that will be 30 upon into 2 into 10 to the power 11. So that will give me what? Minus 4, minus 3, minus 7, 4. So this will be 3 into meter. Is it not? Not meter. Strain is dimensionless. So that's the fraction increase in the length. That's the strain, in fact. Similarly, I can find a stress in this wire. Stress is going to be 10 upon, right, and strain would be stress upon Young modulus. So only difference is in place of 30 we have 10 over here. So strain will be 1/3. So 1 into 10 to the power minus 4. That will be strain. Make a stress 1/3. So strain will also become 1/3. Right. So that's how we can find it. Alright. Let's go to next question. Each of the block P, Q, R shown in figure. Let's draw the figure first. This is the figure. Each of the three blocks P, Q and R has a mass of 3 kg. Each of the wire A and B has got a cross section area 0.05 centimeter square and Young modulus is this. Neglect the friction. Find the longitudinal strain developed in each wire. See, before I calculate longitudinal strain, I will calculate longitudinal stress. The Young modulus is given to me. So once I calculate stress, I will do stress by Young modulus. And in order to find a stress, we have to find tension. Tension in wire A and tension in wire B. Suppose tension in wire A is say T1 and tension in wire B is say T2. Then let's draw the free body diagram. P, you have T1 on this side, and of course you have Mg and normal reactions, they will all balance out. Q, we have T1 on this side, T2 on this side, and of course Mg and normal reaction is always there, right? And then you have R, which is hanging. So you have Mg over here and T2 over here. And suppose the acceleration is A. So if A is the acceleration in downward direction, the acceleration of P and Q will be A in towards right. So this is acceleration A, this is acceleration A, this is acceleration A. Our target is to find T1 and T2. So from here we get Mg is what? 3G. M is 3. 3G minus T2 is 3M. See, they are all in vertical equilibrium, so n minus mg is 0, n2 minus mg is 0. In horizontal direction, we have here T2 minus T1 is 3m. Over here you have T1 equals to 3m. So if I add all these equations, what do I get? I get 3g equals to 9a, or a is g by 3. A is g by 3. Getting a point? So from here we get T1 as 3a, so it is 10 Newton, and then T2 is 10 Newton plus 10 Newton, 20 Newton. So T1 is 10 Newton and T2 is 20 Newton. So if I want stress in A is going to be is T1 upon area of cross section, that is 10 upon, and what's the area of cross section? 0. That's the stress in A. And we want strain, so that will be a stress upon Young modulus, right? So this is going to give me 10 upon Young modulus. What is Young modulus? Young modulus is, so how much this will come? -4, -3, -7, 10 to the power -4, right? Similarly, stress in stress in B is going to be T2 upon area, and T2 is 20 Newton, so it will be twice of this, and similarly strain will also be twice of this. So strain in B is going to be 2 into 10 to the power -4. Strain in B is going to be twice, because stress is twice, tension is twice, so stress is twice. Area of cross section is same. So longitudinal stress will longitudinal strain in B will be twice the longitudinal strain in A. So it is 2 into 10 to the power -4. Okay, that's going to be the strain in B. This is going to be a strain in A. All right, let's go to next question. A wire of area of cross section 3 millimeter square and natural length 50 centimeter is fixed at one end, and a mass of 2.1 kg is hung from the other end. Find the elastic potential energy stored in the wire in steady state. Young modulus is given to you. So you have a wire which is hanged from here, and this is a fixed ceiling, and you have a body of same mass 2.1 kg. So I told you the elastic potential is given by 1 by 2 into stress into strain into volume. So what is the stress? Tension is how much? 2.1 G, that is 21 Newton, right? So stress would be how much? Tension upon area, that is 21 upon, what's the area? 3 millimeter square. So millimeter square means what? In 1 meter you have 1000 millimeter, so -6, 10 to raise to 10 to the power -6 meter square. That's the right, that's the stress. What is the strain? Strain is stress upon Y, that is 21 and upon Young modulus. So that will give me what? That will give me 7 upon 1.9 into 10 to the power -5. That's the strain. What's the volume? Volume is area of cross section into length. Length is 0.5 meter. So this is 1 by 2 into stress. Stress is, strain is, strain by 1.90 10 to the power minus 5, and volume is, right. So this will cancel out. You can calculate it, I think. So this 10 to the power 5 will be upward. It will be like this. Okay, just calculate this. This will give you the answer. This will give you the answer of energy stored in potential, elastic potential energy. The answer will come out to be 1.9 10 to the power minus 4 joule. Just calculate it. Just calculate it for yourself. Okay, let's move to next question. A uniform heavy rod of weight W and cross section area A and length L is hanging from fixed support. Young modulus of the rod is Y. Find the elongation in the rod. See, you have a ceiling over here and you have a uniform rod. This is the rod. This is your rod, right? And we have to find total elongation. We have to find total elongation, right? See, this weight is distributed throughout the rod. Weight is distributed throughout the rod, and tension in the rod is going to be different at different point. Tension at this point is going to be 0 and is going to be highest at this point. Tension depends on, tension at any point will depend on how much of rod is hanging below that point. At this point no part of the rod is below, so tension is 0 over here. At this point all the rod is hanging below this point, so tension is highest. So if I take at a distance of x, if I take an element dx of this rod, this is the element dx, and let's try to find elongation in this part, right? So what's going to be the tension in this element? What's going to be the tension in this element? That would be equal to weight of this section. And what is the weight of this section? That is W upon, W is the total weight, and if I assume that mass is uniformly distributed, then it is W upon L is the mass per unit length, and so W upon L is the weight per unit length, you can say, and this is going to be how much? L minus x. So that's going to be the tension dx. That's going to be tension over here, right? And stress would be how much? Stress would be tension upon cross section area, that is W upon LA, L minus dx. And what's the strain? Strain is delta L upon L. So we don't know what is delta L, but we know dx, and this is going to be, the original length is ds. I want to calculate a strain in this element. So what is the elongation in this element? Suppose the elongation in dx element is delta L, right? Elongation in ds element is delta L, right? Or say, let's call it T of delta L. Suppose elongation in, this is the formula, elongation in dx is d of delta L, length of this element is dx, and that is equal to stress upon Young modulus. So that will be W upon LAY L minus x. So elongation in this dx would be equal to W upon LAY L minus x dx, and total elongation is going to be integral of the elongation in dx, and that will be w upon LA by L minus x dx. And we want elongation in the whole rod, so x goes from 0 to L, so w upon LA by Lx upon x square by 2, 0 to L, so that will give me L square minus, so this is WL upon 2AY. That's going to be the total elongation. Alright, so this is how we can do this question. Okay.